Yes.
But even if they're not, can we say they're not somewhere? The internal and the external.
No, we can't even ask the question if V and W are not subspaces of if they're not subsets of a given vector space. I can't even entertain the question, what is the internal direct sum? It's meaningless.
Okay.
Internal direct sum is only meaningful if we're talking about subsets of a given vector space. So I don't think that, I mean, there might be a way to soup it up so that it's, I just don't, that's what I'm saying. So definition, of course you can take, you know, W1, W2, WS is, you know, S-fold Cartesian product of vector spaces W1, WS over F. So if we can do it for 2, we can do it for S. All right? And there's a theorem, right? Theorem that's kind of obvious. If you take, you know, like, I'll write it out, beta equal to, like, let me write it in the more condensed notation, because I think you'll understand. So if I take the basis for 1, the Cartesian product with 0. Well, let me just write 0 if that's okay. Oh, fine. That unioned with, well, 0 Cartesian product with beta 2. I don't know. I'm going to get into trouble here.
Can we write it more condensed?
I'm just worried about I'm mixing elements and sets or something. So, and I fuss about you guys doing that, so I shouldn't. But if, let me say 1, 1, and then 0, 0, dot, 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 dot. Eventually, you get to W1, M1, and then zeros. And then finally, we finally get to the S. That was supposed to be S, my bad. We finally get to the S, one of these lists. We get to W sub S1. Oh, my bad. Zeros. W sub S1. End of the list, right? And then finally, zeros all the way. 0. And then finally, the last basis element of the last subspace, W sub S, M sub S. All right, where of course I'm using, you know, W sub I J good grief, 1 less than or equal to J, oh, my bad, J I sub J, I suppose. 1 less than or equal to J less than or equal to S. 1 less than or equal to I sub J less than or equal to M sub J, as the basis elements for W1, W2, WS respective. My point is, if you can do it for 2, you can do it for S. And so you see that the dimension of the Cartesian product of S subspaces is the sum of the dimensions, right? All right. And then definition, W1, W2, dot, 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 W, let's say K, are subspaces of V, all right? If they're subspaces of V, then we say V is an internal direct sum of the subspaces. And we write V equals W1 direct sum W2 direct sum WK if and only if V is equal to W1 plus W2 plus dot 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 plus WK, where that has the obvious meaning extending from 2 to K, right? You just take sums of things, sums of elements from each one, right? Oh, my bad. I'm not following my own definition. I am so sorry.
Do we have to say if they're all disjoint?
Well, listen. The definition I was about to write down was that this, if this and Wi intersect W, well, let's say the direct sum, the sum, rather, the sum, J not equal to I from, J equals 1 to K, J not equal to I of W sub J is equal to 0. This means that W1 for 3, all right? W1 intersect W2 plus W3 is equal to 0. W2 intersect W1 plus W3 is equal to 0. W3 intersect W1 plus W2 is equal to 0. We need independence of all the subs. This is how we characterize independence of subspaces when there's 3 or more. That reduces to simple intersection being 0 when we have 2 subspaces. But for 3, we have to be more careful. So that is a potential definition. It's actually not the definition in my notes. What's the definition in my notes? Definition in my notes is that for each x in V, right, there exist unique x sub I in W sub I for I equals to 1 to dot 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 K, such that what? Such that x is equal to x1 plus x2 plus dot 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 plus x sub k. That's the definition I've given in my notes. That's the characterization of internal direct sum I've given in the notes, is that there's a unique decomposition of each vector as a linear combination of vectors from each of the respective subspaces. Right? That's so let me call this number 1. This is number 2, right? There are actually 4 quite different looking characterizations of the independence of the subspaces. Here's another one. 3 is that V, I think it's, just a second here.
The unique thing guarantees that they're independent.
Yes, it does. The other one is that for again, for xi in wi such that x equals to x1 plus x2 plus dot 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 plus xk equals to 0, all right? If that implies x1 equals to 0, x2 equal to 0, dot 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 dot, xk equals to 0, In other words, you can only build 0 for for the whole space as a sum of the zeros in the subspaces. There's no way to build 0 except from the 0 vector in each subspace. That's another characterization. Another equivalent characterization is that if beta I is basis for wi, then beta equal to beta 1 union beta 2 union union beta s, beta k rather, is basis for v. So they're independent subspaces. If you can take a basis for each subspace and then union those all together and you get a basis for the whole space, that's another way to characterize independence of subspaces. Any one of these could be taken as the definition of internal direct sum. But perhaps the most bestest, the extra most bestest maybe, make myself hungry, is that the mapping, I've called it pi, but I'm not sure pi is really, let me call it eta. The mapping eta from the Cartesian product of W1, W2, Wk, right, to V, defined by eta of x1, x2, xk, equal to what? I'm taking a vector in W1, a vector in W2, a vector in Wk. I'm combining them to give a vector in V. This mapping eta I'm defining right now, which I've called pi in the notes, is actually a isomorphism. What is the mapping?
Mapping to be x1 plus x2 plus.
Yep, that's it. That is the isomorphism.
That makes sense. Okay.
Right. Now the thing is, if we have an endomorphism, right? If we have a mapping from V to V, and if that mapping has every one of these W's as an invariant subspace, then what happens to the matrix of that transformation, if you have a basis which respects the subspace decomposition, is you get a block diagonal decomposition, where the blocks are speaking to the action of T on each one of the subspaces respectively. Now I prove the equivalence of these on my lectures that I gave on March 8th and March 10th of 2017. I apparently don't have it in the notes. But this is one of the places where that student I worked with before, Kang, sometimes he just made me very happy, because in my notes before Kang, I had all of these, but I didn't have the 0. And like in class, Kang was like, "Sir, there's another characterization of independent subspaces. 0 has a unique representation." And I was like, "Oh, very good, actually." I mean, so like, Kang impressed me. But yeah. Let me give you an example of this, and we'll stop for today, if you don't mind. Can I go a little bit more? Yeah. So let's see here. We could take, this is example 2. I don't know. Actually, did I do an example yet today?
Maybe one.
I don't know if I did the subspace thing. That's right, yeah. So if I let V equal to, let's say, R 3 by 3, right? And I'm going to look at this as W1. I'm going to show it's W1 directs W2, where W1 is equal to, you know, A in R3 by 3, such that A transpose equals to A, and I'll let W2 equal to, you know, A and R3 by 3, such that A transpose is equal to minus A, right? So the symmetric and the anti-symmetric 3 by 3 matrices. So first of all, if you take any matrix, right, you can write it as 1/2 A plus A transpose plus 1/2 A minus A transpose. That's an identity. And so this, of course, is an element of W1. And this is an element of W2. You can check that those are respectively symmetric and anti-symmetric matrices. Consequently, this proves what? That W1 plus W2 is the whole vector space, right? Now, if A is an element of W1 intersect W2, then A transpose is equal to A, and it's also equal to, A transpose is also equal to minus A. Therefore, A is equal to minus A, which implies A is equal to 0, which of course tells me W1 intersect W2 is 0. So, happy day. V is the direct sum decomposition of W1 and W2. And I mean, if we wanted to, you know, you can take basically eta of what? Like a typical element of W1 looks something like, you know, A, B, C, D, E, F. These are repeats, yeah? And then typical thing in the other one would be 0, x, y, minus x, 0, z, minus y, 0, minus y, minus z, 0. And so then, if you add these together, you get, you know, A, B plus X, C plus, oh, this is funky. I've never done this before. I don't know what this means. I don't know what this means, Ernesto. I mean, it is what it is, but how to think about this formula I'm writing down. I'm not sure what's the right way to think about it, except to say that when you look at E minus, like you look at these funky looking ones, right? So if you think through this, since look at it this way, B plus X and B minus X are free variables, right? These, I mean, if you think about it, you could replace these with just a pair of free variables. C plus Y, C minus Y, these could be replaced with a different pair of free variables. I mean, this is equivalent to just having an arbitrary 3 by 3 matrix, you know? I don't know. I'm not sure this is that interesting a calculation. What's more interesting, right, is if you look at the transformation T of, let's say, matrix A equal to, well, let's say equal to A transpose, right? And so if you look at T restricted to W1 of A, what's it equal to? What's T restricted to W2 of A? What's that equal to? Well, W1 is the set of symmetric matrices, right? So if T is the transposition map, well, it's just equal to A again, right? And this one's just equal to minus A again. Which means that like the matrix of T with respect to W1, and I'll leave off the basis because it doesn't matter what the basis choice is actually in this case, kind of funny. Well, the bases are just identity minus identity. Now, specifically, W1 is 6-dimensional. So this is the 6 by 6 identity. This is the 3 by 3 minus identity. And so if we looked at the matrix of T with respect to a basis, which is, you know, like beta 1 union beta 2, right? Then what we'd have is block diagonal, right? You got I6 up here, and you got minus I3 down here, and you got zeros on the off diagonal. It actually doesn't matter what you make the basis. I think in this case, in this rather special case, it doesn't matter what you make the basis for W1. I think you're going to end up with the identity matrix there and minus identity matrix there, just because I think the identity transformation has the same matrix in any choice of basis, and the minus identity as well, because we're using the same basis in the domain and the codomain. So like, I think it has to be that the matrix of the identity transformation is the identity matrix. And same is true for minus. So like, of course, we could pick a basis for W1 and a basis for W2 and sort through it, but we don't need to. So anyway, that's just, I usually put something like this on my linear final. Anyway, that's all for today.